NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will learn how to factor the difference and the sum of nth powers of two terms using a compact general formula. We will also note useful divisibility rules, apply substitutions with nth roots, and work through examples. Finally, we will try a quick challenge together. Step 1. Apply the difference of nth powers formula. It says, open parenthesis, a minus b, close parenthesis, times the sum, a to the n minus 1 plus a to the n minus 2 times b, and so on, up to b to the n minus 1 equals a to the n minus b to the n. Intuitively, if you distribute a minus b across this long sum, the middle terms cancel in a telescoping way, leaving only a to the n minus b to the n. Step 2. Apply the sum of nth powers when n is odd. If n is odd, n equals 2k plus 1, then open parenthesis, a plus b, close parenthesis, times the alternating sum a to the n minus 1 minus a to the n minus 2 times b plus a to the n minus 3 times b squared, and so on, up to b to the n minus 1 equals a to the n plus b to the n. Notice the alternating signs inside the second factor. This alternating pattern is what makes the cross terms cancel, leaving a to the n plus b to the n. Step 3. Recall the divisibility properties. First, a to the n minus b to the n is always divisible by a minus b, whether n is even or odd. Second, a to the n plus b to the n is divisible by a plus b only when n is odd. Third, a to the n plus b to the n is not divisible by a minus b. Step 4. Use substitutions with nth roots. Let a equal the nth root of x, and b equal the nth root of y. This allows us to rewrite x minus y, and, when n is odd, x plus y in factored forms. Step 5. Express x minus y and x plus y using nth roots and the sum of powers factors. For n even, x minus y equals open parenthesis nth root of x minus nth root of y, close parenthesis, times the sum of n minus 1 terms built from x and y. For n odd, x plus y equals open parenthesis nth root of x plus nth root of y, close parenthesis, times the alternating sum with n minus 1 terms. Step 6. Let us apply the formulas in concrete examples. Example 1. For n equals 2, x minus y factors as open parenthesis square root of x minus square root of y, close parenthesis, times open parenthesis square root of x plus square root of y, close parenthesis. Example 2. For n equals 3, the difference x minus y factors as open parenthesis cube root of x minus cube root of y, close parenthesis, times open parenthesis cube root of x squared plus cube root of xy plus cube root of y squared, close parenthesis. Example 3. Also for n equals 3, the sum x plus y factors as open parenthesis cube root of x plus cube root of y, close parenthesis, times open parenthesis cube root of x squared minus cube root of xy plus cube root of y squared, close parenthesis. We display the word example, then the problem in bold orange latex. Step 1. OCR and text extraction. We recognize the expression as open parenthesis to a minus 1 close parenthesis times open parenthesis 16a to the 4th plus 8a to the 3rd plus 4, a squared plus 2, a plus 1 close parenthesis. All symbols are standard, so no replacements are needed. Step 2. Structural analysis. The second factor matches a geometric sum of powers. This signals the classic factorization pattern. Open parenthesis x minus 1 close parenthesis times open parenthesis x to the n minus 1 plus x to the n minus 2 plus dots plus 1 close parenthesis equals x to the n minus 1. Here we set x equal to 2a and n equal to 5, because x to the 4th plus x cubed plus x squared plus x plus 1 contains 5 terms. Step 3. Apply the rule directly. Replace x by 2a and n by 5 to get open parenthesis 2, a close parenthesis to the 5th minus 1. Step 4. Simplify the power. Open parenthesis 2, a close parenthesis to the 5th equals 32a to the 5th. So the expression becomes 32a to the 5th minus 1. Final answer shown in green. Example. Factor the expression using the difference of powers pattern. We will strictly follow the two-step structure shown. First, rewrite as a difference of fourth powers. Second, simplify each power and write the final result. Here is the rule we will apply. It is the difference of powers identity. Left parenthesis x minus y right parenthesis times the series x to the n minus 1 down to y to the n minus 1 equals x to the n minus y to the n. Step 1. Rewrite as a difference of fourth powers. Start from the original product. Replace the long polynomial by the four-term sum x cubed plus x squared, y plus xy squared plus y cubed, with x equal a squared and y equal 3b squared. Then, by the rule, the product equals x to the fourth minus y to the fourth, that is left parenthesis a squared right parenthesis to the fourth minus left parenthesis 3b squared right parenthesis to the fourth. Quick challenge. Can you say out loud which identity we just used? Step 2. Simplify each power. We simplify left parenthesis a squared right parenthesis to the fourth to a to the eighth. Next, simplify left parenthesis 3b squared right parenthesis to the fourth. That equals 3 to the fourth times left parenthesis b squared right parenthesis to the fourth, which is 81b to the eighth. So the overall expression equals a to the eighth minus 81b to the eighth. Factor the expression exactly as written, then simplify. We start by recognizing the structure. Step 1. Recognize a sum of fifth powers. We use the sum of powers rule. Then identify x equals 2a, y equals 3b, and n equals 5. Step 2. Simplify by evaluating the powers and coefficients. 2a to the fifth is 32a to the fifth. 3b to the fifth is 243b to the fifth. Now problem 2. Factor and simplify following the same structure. Step 1. Recognize a difference of sixth powers. Apply the rule with x equals a squared, y equals b squared, and n equals 6. Step 2. Simplify the powers. A squared to the sixth is a to the 12th. B squared to the sixth is b to the 12th. Great job. Final answers in green. First expression simplifies to 32a to the fifth plus 243b to the fifth. Second expression simplifies to a to the 12th minus b to the 12th. Welcome. In this example, we will process a math problem and produce a fully detailed, step-by-step solution. In English, we will follow a clear sequence with rule boxes, colored highlights for changes, and a final summary. First, we display the word example as a label for our problem. Our problem statement, shown in bold orange, is to prove the classic factorization identity. A to the n minus 1 equals open parenthesis a minus 1 close parenthesis times a to the n minus 1 plus a to the n minus 2 plus dots plus a plus 1. Quick challenge. Can you predict our first move? We will define a helpful sum to organize the terms. Step 1. Define the series s as 1 plus a squared, and so on up to a to the power n minus 1. Step 2. Multiply both sides by a. This shifts each power up by 1. Notice the change from s to as, and the last term becomes a to the n. Step 3. Subtract the first definition from this new equation. On the left, we get open parenthesis, a minus 1 close parenthesis times s. On the right, everything cancels except a to the n minus 1. Step 4. Now solve for s by dividing both sides by a minus 1, assuming it is not equal to 1. Step 5. Substitute our definition of s, which is 1 plus a squared up to a to the n minus 1, and multiply by a minus 1. We obtain the desired factorization. Great job completing the proof. Take a moment to reflect. Could you have predicted the subtraction step that cancels the middle terms? Important note, this derivation assumes a is not equal to 1. If it equals 1, both sides are 0, and the identity still holds trivially. Let us summarize the key ideas. We defined s multiplied by a, subtracted to form a minus 1 times s, then solved for s and substituted to obtain the factorization. In this lesson, we will approximate the cube root of 997 using the binomial approximation rule for small x. Here is the problem we want to solve, the cube root of 997. First, recall the rule for small x. If the absolute value of x is less than 1, then 1 plus x to the power n is approximately 1 plus n times x. Equivalently, the nth root of 1 plus x is approximately 1 plus x divided by n. Next, we express 997 using a nearby perfect cube. Notice that 1000 is 10 cubed. So write 997 as 1000 minus 3. That is 1000 times the quantity 1 minus 3 over 1000. Now take the cube root of both sides. The cube root of 1000 is 10. So the cube root of 997 equals 10 times the cube root of 1 minus 3 over 1000. We will now apply the approximation to the cube root factor. Here x equals negative 3 over 1000 and n equals 3. So the cube root of 1 plus x is approximately 1 plus x divided by 3. That equals 1 minus 1 over 1000, which is 0.999. Now multiply by 10. Therefore, the cube root of 997 is approximately 10 times 0.999, which equals 9.99. For intuition, here is a zoomed number line around 10. Because 997 is just 3 less than 1000, its cube root should be just a little less than 10. The value 9.99 is 1/100th below 10, which matches our expectation. Quick challenge. Pause and estimate the cube root of 1000 and 1 using the same idea. Think, 1000 times the quantity 1 plus 1 over 1000. Using the rule, the cube root is approximately 10 times 1 plus 1 over 3000, which equals about 10.0033. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.